All right. So last time we were categorizing molecules as by being either aromatic, anti-aromatic, or non-aromatic. All right, and you just kind of trusted me with regards to aromatic being super stable, anti-aromatic being super unstable. Now we're going to explore this idea of the stability of these compounds a little bit more. All right, so like we said, aromatic meant super stable molecules. All right, which by that we mean unreactive. All right, when something is nice and super stable, it doesn't react with other molecules. And this was really apparent from studying benzene early on. All right, again, we lumped this into a different category than our regular old alkenes, because regular old alkenes, so for example, cyclohexene, will undergo these addition reactions. So we take HBr, for example. We get this addition product where a hydrogen's added to one side and a bromine's added to the other side. Okay. We talked about this reaction even more with regard to our conjugated dienes, right? These addition reactions. Cool. So then if you take benzene, which on the face of it you would think, well, we got a bunch of pi bonds here. Shouldn't this do the same thing? Under the exact same conditions, there is no reaction. All right, so in comparison to our normal old alkenes, benzene is this super stable molecule, right? Doesn't undergo these same reactions. You have an anti-aromatic compound. That is super unstable, meaning highly reactive. In fact, these anti-aromatic compounds are kind of difficult to study because they end up reacting with themselves, undergoing, say, a Diels-Alder reaction. So you can't really isolate them very efficiently. All right, so you just kind of trusted me that aromatic was super stable and anti-aromatic was super unstable. All right, but why? For that, we're going to need to turn to what's called molecular orbital theory. All right, this is how we're going to explain why aromatic is good and stable and anti-aromatic is bad and unstable. I'm going to be dead honest with you. It's not going to be the most satisfying explanation in the world because molecular orbital theory is this big, complicated, like quantum mechanical kind of base theory, and we don't do any math in this course, right? So we're not even going to really look at the quantum mechanics of it. You're just kind of going to trust me about this whole thing. So this is how we're going to explain it, and you're going to be like, okay, great, that was not the most satisfying explanation in the world, but nonetheless, that's how we explain the difference between anti-aromatic and aromatic compounds, is using what's called molecular orbital theory. All right, so what the heck is molecular orbital theory? All right, again, it is a quantum mechanics based theory of how bonds form. Right, so we're going to talk about the orbitals that these electrons live in when they form a chemical bond, right? When they make a molecule. All right, and how this happens is our atomic orbitals Remember back from general chemistry, you talked about how a carbon atom was a 1s2, 2s2, 2p2, right? You learned the electron configuration for those atoms. Those were the atomic orbitals. Those are where the electrons live if I'm holding a carbon atom when it's all by itself. When that carbon atom goes and forms new bonds, those electrons mix together. Those atomic orbitals mix to form what we call molecular orbitals. All right, so those molecular orbitals, that is where bonding electrons live. All right, and then kind of the simplest principle here, the number of atomic orbitals that we mix together is equal to the number of molecular orbitals that are formed. All right, so first thing we're going to do, we're going to talk about aromatic compounds here, but let's just look first at a conjugated diene. In our conjugated diene, remember what makes this so special is each one of these carbons has a p orbital. They overlap to form these pi bonds, but what makes the conjugated diene so special is actually all of these p orbitals are connected, and those electrons, those pi electrons, are delocalized across all four of those carbons, right? That's what made this conjugated diene so special. So what we're going to see here is these four p orbitals. They're going to mix together to form four new molecular orbitals. All right, and if we make a little plot here, where we're going to plot each of those orbitals relative to their energy level, what we would see is those four new molecular orbitals, they're spaced out in increasing energy here. All right, so these are my four new molecular orbitals. And we learned how to fill in these energy diagrams with electrons back in general chemistry, and we're going to follow the same rules that we did then. All right, we have four delocalized electrons, right? 2 pi bonds of delocalized electrons. So we're going to fill in our diagram here with 4 electrons. We always start at the lowest energy level and work our way up. And remember, we can fit 2 electrons in an orbital, but they have to have differing spins, right? 1 spin up, 1 spin down. So if we're going to fill in this diagram with 4 electrons here, we're going to fill in those lowest 2 molecular orbitals. All right, the lower energy orbitals are what we call our bonding orbitals, and the upper energy ones are what we call anti-bonding orbitals. All right, and so what we've just shown here is we have 4 electrons fully occupying those bonding orbitals, and there's nothing up here in those anti-bonding orbitals, that's good. That's nice and super stable, right? So a molecule that has full bonding orbitals and no electrons in their anti-bonding orbitals, that's a nice stable molecule. And everybody's like, yeah, totally. Yeah, duh. All right, again, trust me. All right, this is how we're sort of depicting why these things are in this increasing pattern here, because that's what quantum mechanics says, right? So we made this little simple staircase here. In truth, you would have solved a big, ugly math equation, and it would have told you what exactly these energy levels were, all right? But it turns out for our conjugated dyene, they are very simply just this increasing order here. And again, we have these full bonding orbitals, which is nice and stable. All right, now let's look at an aromatic molecule. Okay, and we're going to take benzene. All right, so how do we draw? So we're going to do the same thing. This is our goal, is to make our similar MO diagram where we represent those molecular orbitals and their relative energy levels. All right, but how do we orient those energy levels? All right, so how do we draw that MO diagram? All right, it's gonna drive me nuts, it's ugly. Okay, so first thing we're gonna do is we're gonna take the shape of whatever it is that we're working with, whatever cyclic structure that we're working with. We're gonna take that shape and we're gonna orient it such that one of those corners is pointed down. All right, so we're going to orient our shape with one corner pointed down. Okay, so what do I mean by that? Okay, our normal way of, at least for me, the normal way in which I draw these cyclic structures that have 6 carbons is to have one of those corners pointed down, right? That's just how I tend to draw it on the page. Different from, say, how I tend to draw a 5-membered ring, where on the bottom here, I tend to draw it such that it's flat on the bottom. Importantly, what I would have to do if this was a 5-membered ring then is then turn it such that one of those corners was pointed down, right? So we're going to take whatever shape we're working with and we're going to turn it such that one of those corners is pointed down. All right, now we're going to draw our molecular orbitals, those energy levels at every corner. So down here at the bottom, that's an energy level. These corners are energy levels. These corners are energy levels. And this one at the top is an energy level. All right, and then lastly, we're going to fill in with our correct number of delocalized electrons. All right, so benzene here has how many delocalized electrons? 6, right? So each one of these pi bonds contains 2 electrons. These are what are delocalizing around that ring. So what I'm going to do is I'm going to take this diagram here and I'm going to fill it in with 6 electrons. All right? Like we said, we're going to start at our lowest energy level. That's where we're going to fill in first. So 1, 2. Now we get to these two energy levels, and they're tied. All right, so if you remember back from your filling rules, what you're going to do is you're going to half fill these energy levels first, then you go back and double up. Oh, something happened there. All right, so I guess just to start over here, filling in my diagram, I'm going to fill in my bottom energy level first. Then I'm going to go through and half fill these two because they're equal energy before going back and doubling up. All right, and what we're going to see with our aromatic compounds is that we have these fully filled bonding molecular orbitals, and again, fully filled means nice and super stable. All right, so what our energy diagram here showed is that we have these fully filled bonding orbitals, which implies that this compound is nice and super stable. All right, so to draw our molecular orbital diagrams, we're going to take whatever polygon we're working with, whatever our ring structure is, and we're going to orient it such that one of those corners is pointed down. Then at each one of our corners, we're going to draw these molecular orbitals, draw these energy levels, and then we're going to fill it in with the proper number of delocalized electrons. And what we're going to see is that for our aromatic compounds, we have these bonding orbitals, these lower energy orbitals that are nice and filled in, which makes that compound super stable. All right, now, why did I take this shape and turn it on its side and draw these energy levels? Again, it's a solution to a big, ugly quantum mechanics problem. The fact that this little trick works is kind of a miracle in and of itself, all right? So this is just a stupid little trick that we can use to help us explain this big, ugly quantum mechanics theory, right? Why does it work? Go ask the math. It's a big, ugly problem, all right? But it does work. So we can use this little trick of taking this shape and turning it such that one point is facing down, drawing energy levels on these corners, and this represents the molecular orbital diagram of that particular molecule, right? The relative energy level of those molecular orbitals in this little shape here in our molecule. All right, so now we're going to do the same thing, but we're going to look at our anti-aromatic molecule. So let's take an example of an anti-aromatic molecule. We're going to do cyclobutadiene. This angry little square here. All right, and again, my goal is to create this plot that shows the relative energy levels of those molecular orbitals. All right, so I'm going to take my square here, and what am I going to do to it first?
Put it on the corner down.
Yeah, I got to turn it, right? So I got to twist this thing around such that one of those corners is pointed down, right? That was step one, is to turn your shape such that one of those corners is pointed down. Now I'm going to draw energy levels at all of my corners here. All right, and then I'm going to fill these in with electrons. How many electrons am I going to fill in? 4, right? My 2 pi bonds are delocalized here, so I got 4 electrons to fill in. All right, importantly, I'm going to fill that lower energy level first. So I got 2 more electrons to put in. And remember, because these two are now equal energy, we have to go through and half fill first before we can double up. And after I half fill those orbitals, I'm done. That's all the electrons that I have to put on the board. All right? So what we see here is in my molecular orbital diagram for this anti-aromatic compound, we have these half-filled molecular orbitals. And half-filled molecular orbitals are super mad, all right? In the same way that we said that fully filled bonding orbitals were nice and super stable, these partially filled bonding orbitals are super unstable. Okay, electrons don't like to be unpaired. You guys talked about radical reactions in the first semester, these unpaired electrons being angry and super reactive. It turns out that half-filled or unpaired bonding electrons are just as angry and reactive. All right, so in our anti-bonding orbitals, we have these half-filled molecular orbitals. Half-filled, we're going to call them bonding orbitals. Which are then super unstable. All right, cyclobutadiene is a molecule that you cannot really isolate because it ends up reacting with itself. It's just highly reactive because it has these half-filled bonding orbitals, which means that it's super unstable, right? These unpaired electrons. So if you remember back when we were talking about rules for aromaticity, there was that first rule about it being a fully conjugated ring. And that, at least to me, kind of makes sense, right? Okay, yes, the electrons need to be able to delocalize around that ring, so there has to be those p orbitals for those electrons to move into. Check, check. We know delocalization is stable, right? That second rule really came out of left field, that odd number of electron pairs. Where the heck did that come from, right? Why do you have to have an odd number of electron pairs? If it's an even number of electron pairs, all of a sudden it's really bad. Why is that? This is what, and again, I know it's not that satisfying, but this is what our molecular orbital theory helps to explain here. Turns out that if you have an odd number of electron pairs, you'll have these half-filled molecular orbitals. I'm sorry, you have an even number of electron pairs. If you have an anti-aromatic compound, you'll have these half-filled molecular orbitals, which are bad. And if you have an odd number of electron pairs, like an aromatic compound, you'll have these fully filled molecular orbitals, which is good. All right, so that second rule, where does that come from? Odd number is good, meaning fully filled molecular orbitals. Even number is bad, meaning half-filled molecular orbitals. All right, so that's our explanation as for why aromatic compounds are stable and anti-aromatic compounds are super unstable. All right, and again, we have this cute little trick of taking that polygon and turning it on its side to figure out what those energy levels are, but really this is a big, ugly quantum mechanics problem about the energy of those electrons, right? So this is just kind of a little trick to show that how that works. All right, cool. So we're going to take a really random turn here in this chapter. There are two reactions that are kind of tacked on to the end here, and so these are how we're going to close out this chapter, talking about reactions at what we call the benzylic position. All right, so first of all, benzylic position, kind of analogous to the allylic position when you were talking about alkenes, but the benzylic position is the carbon one removed from that benzene ring. All right, this is our benzylic position here. Not on the ring, not any further away, but just one removed from that benzene ring. All right, so there's two reactions that we're going to talk about that take place at that benzylic position. The first one is oxidation of that benzylic carbon. So first of all, if we take this guy here, methylbenzene, but we don't call it methylbenzene, what's the name? toluene. I don't even know how you're supposed to say it correctly. It's got way too many vowels in there, all right? But yes, toluene is how I say it, but remember we have a special name for our methylbenzene. And we hit it with some oxidation agent. Truthfully, there are a lot of different oxidation agents that you can use, especially nowadays. It turns out that the ones that they used to use back in the day were terrible for the environment, so there've been some new fancy ones that have come on board. What we're going to use is what's in our textbook, which is kind of an old school one. You can tell because it's got chromium in there. Chromium is just a metal that is famous for oxidation, but is also terrible for the environment. Nonetheless, this is the one in our textbook, so sodium dichromate. You use this with sulfuric acid, dilute sulfuric acid. All right, and what we're going to see is we're going to fully oxidize that benzylic carbon. All right, and if you're having like terror flashbacks to general chemistry, oxidation numbers were such a pain in the butt to calculate, all right? Good news is that in organic chemistry, when we're talking about oxidation, it's really straightforward. We're creating more carbon-oxygen bonds, all right? So what we mean by oxidizing this benzylic carbon is we're going to create more carbon-oxygen bonds. We're going to create the maximum number that we can, which means creating a carboxylic acid group. All right, so in organic chemistry, when you hear oxidize, you're going to think creating more carbon-oxygen bonds. If we fully oxidize something, we've created the maximum number of carbon-oxygen bonds that we can, or this carboxylic acid group. All right, so if we take toluene and we hit it with this oxidation agent, we fully oxidize that benzylic carbon. What happens if we have a longer hydrocarbon chain, something like propylbenzene? All right, if we hit this with our oxidation agent, turns out we get the exact same product. All right, so it'll actually cleave off any extra carbons in order to fully oxidize that benzylic position. All right, the only catch here is that this reaction requires a benzylic hydrogen to occur. So if we had a molecule that doesn't have any benzylic hydrogens, and we hit it with that same oxidation agent, we would get no reaction. All right, again, this requires a benzylic hydrogen. Okay, now why does it require a benzylic hydrogen? We don't know. All right, so this is a good example of a reaction where we don't look at the mechanism for. Right? We talked about a bunch of reactions earlier in this chapter where we have our reaction mechanism, our electrophilic addition reactions. We know the reaction mechanism that helps us explain our reaction. This is an example of a reaction that we're going to cover where we don't have a mechanism for. Right? So you're just going to trust me here that this reaction requires a benzylic hydrogen. So if there's no benzylic hydrogen, you have no reaction.
Does it just require one benzylic hydrogen?
Yep, as long as there's one on there. Yep. So the only thing you couldn't have is a quaternary carbon in that benzylic position. Then there would be no reaction that occurs. All right, so our last reaction that we're going to cover for this chapter, close out this chapter, is a benzylic bromination reaction. this uses what's called N-bromosuccinimide. Alright, and that's the following molecule. Okay, so this is our reagent that we're going to be using here, N-bromosuccinimide, or what's just referred to simply as NBS. So if we take our NBS and we react it with toluene, what we're going to see is we're going to brominate that benzylic position. Right, aka we're going to add a bromine to that benzylic carbon. Likewise, if we take propylbenzene, and add NBS, we're going to brominate, put a bromine on that benzylic carbon, and specifically that benzylic carbon, right? The one that's one removed from that benzene ring. Okay, now one thing we want to note here is we don't draw our implied hydrogens, right? But if we did, we would convince ourselves that this is a substitution reaction. We're taking a hydrogen off of that benzylic position and replacing it with a bromine, right? We're substituting our hydrogen for a bromine on that benzylic position in this reaction. Okay, so this is another reaction where, again, we don't know our mechanism for, but you're just going to trust me that it requires a benzylic hydrogen for that substitution reaction to occur. So if, again, we had no benzylic hydrogen and we hit it with our NBS, we would have no reaction. Oops. All right, so we have our benzylic bromination reaction using this N-bromosuccinimide, this thing here. It will brominate a benzylic carbon in a substitution reaction where it replaces the hydrogen with a bromine. If you don't have a hydrogen, though, you don't have any reaction. All right, similar to when we were looking at before, our oxidation of that benzylic carbon, we can fully oxidize that benzylic carbon to a carboxylic acid group. But just like before, if we don't have a benzylic hydrogen, we don't have any reaction. All right, so these are two reactions that we kind of tacked on to the end of this chapter. They occur at that benzylic carbon, one removed from that benzene ring. They are going to come up again in the next chapter as well. All right, so we're kind of laying some groundwork for what we're going to talk about later this week. Okay. Cool, so we got these two random reactions, oxidation of that benzylic carbon and bromination of that benzylic carbon. All right, and what we started the day doing was talking about this molecular orbital theory, drawing these MO diagrams of our aromatic and anti-aromatic compounds. Aromatic compounds will have fully filled bonding orbitals, which is nice and stable. Anti-aromatic compounds will have half-filled bonding orbitals, which is bad, unstable. And that's all I got for you. Cool. Done with this chapter. All right. And we'll pick up with the next one next class period. We're going to call it early today.